In this video, I'm going to discuss the probability of the origins of life on a universal scale and what this means for the creationist argument against abiogenesis. I know I'm deviating from my stated purpose of only discussing astrophysics, but this form of argument is a very real part of the field of astrobiology which is tightly coupled with astrophysics. It is commonly heard in intelligent design argument that the chances of a bunch of molecules randomly assembling themselves into some sort of pre-life self-replicating structure, what scientists call abiogenesis, are astronomical. A commonly heard number is 1 in a trillion. That is 1 over 10 to the 12th. I don't know why 1 in a trillion seems to be the number of choice, but you will hear it more than any other number. Not just for abiogenesis arguments either, but for any time they want a high probability of something not happening. So before I begin this video, I would like you to write down whether you think that is a reasonable number. If you think it is too probable, write that down. If you think it is not probable enough, write that down too. If you think it is spot on and the creationists have it right, write that down. Go ahead, I'll give you a few seconds. Pause the video to find paper if you need it. Now, as you may have guessed from my discussion of 1 trillion, this video will be dealing with numbers. Really big numbers. But I'll be taking you through those numbers one at a time. For the sake of humoring the creationist argument, we will assume 1 in a trillion to be a correct presumption of the chance of abiogenesis occurring on a planet which is capable of sustaining life. There's no real scientific basis, but it is as good as a number as any for our purposes. So let's begin. There are about 100 billion galaxies in the known universe based on the Hubble Deep Field images, which took pictures of a tiny fraction of the night sky and how many galaxies were visible, and then extrapolated it into how many would be visible across the entire sky. Actually, more recent deep field images, with better technology, estimate the number to be 125 billion, but we will, again, take the number that is more favorable for the creationists. In each of these galaxies there are about 100 billion stars. This approximation is obtained by using Newton's version of Kepler's third law to determine the mass of the galaxies. Other mass determining techniques which are more complex are used as well. We can compare this to the average mass of known stars in our own galaxy, the Milky Way, and figure out how many stars ought to be in the other galaxies. Since the Milky Way is a rather large galaxy, with about 2 billion stars, we have a plenty large sample size to be estimating average star masses. Now, we can take these two numbers to determine how many stars there are in the known universe. 100 billion stars is more easily stated as 10 to the 11th. Now 10 to the 11th times 10 to the 11th, since there's 100 billion stars in each galaxy, and there's about 100 billion galaxies, is 10 to the 22nd. It is quite simple. Now, not all of these stars are even feasibly capable of sustaining life. All of the binary systems, which constitute about half of known stars, are right out. So we'll have about 50% of stars eligible for life. However, out of all the single star systems, not all the stars are exactly winners. There are several spectral types which could potentially sustain life under the right conditions, but the only spectral type star that we've actually observed to sustain life is the G spectral type of our own star, Sol. So we will again give the creationists the benefit of the doubt and assume that only G spectral type stars, which account for about 1/13 of all stars in the universe, are capable of sustaining life. If we divide the 50% that we have now by 13, we are left with about 3.8% of stars capable of sustaining life. Of course, not every star is going to have planets in its habitable zone, that area around the star where temperature is right for liquid water to exist. And as all life that we have so far observed requires water, it is assumed that any life-sustaining planets must exist in this habitable zone. Now, the habitable zone has a bit of a fudge factor in it, as the albedo of a planet, the amount of light reflected by the planet, is very variable, and a planet with a much higher albedo could exist closer to a sun at similar temperatures to our own Earth. However, we will again give the creationists the benefit of the doubt and assume that for life to be sustained, conditions must be identical to our own Earth, which gives you a habitable zone extending from about 0.7 AU to 1.5 AU, and 1 AU is the distance from the Earth to the Sun. And this gives us a 0.8 AU wide zone. When you consider that our solar system has 4 planets in its first 1.6 AU, an average of 1 planet per 0.4 AU, it almost seems that we should have 2 planets in this habitable zone. But I will yet again give the creationists the benefit of the doubt and say that not only does our planetary density not suggest that an average of 2 planets should exist in this habitable zone, but that our system is in fact an exception to the rule, and that most worlds would have only 1 planet inside their frost line, meaning that there's only a 1/2 chance of a planet existing in this zone. If you examine nebular theory, this is a completely errant assumption, but I'm in a nice mood today. That cuts out 1/2 of 3.8, leaving us with 1.9. We'll round up to 2 for the sake of cleanliness. So we have a 2% chance that any star which is in the universe will have a planet around it, with conditions potentially hospitable to life. When we multiply this by our 10 to the 22 stars, we get 2 times 10 to the 20th. Stars that could potentially sustain life because they have planets around them with the right conditions. I'd like to take a moment to go back to the beginning of the video and remember that we assumed life has a 1 in a trillion chance of existing on a planet with hospitable conditions. Keep in mind that this is 1 in a trillion chance of any life appearing within the 10 billion year period of a G-type spectral star's main sequence. When we divide 2 times 10 to the 20th, a number of planets hospitable to life, by a trillion, a percent chance of any of those planets actually having abiogenesis occur on them, we get 2 times 10 to the 8th. That's right, based on creationist numbers, which supposedly show abiogenesis to be nearly impossible, it is something approaching an absolute certainty. And that's with all of the odds stacked in the creationists' favor, with me blatantly handing the creationists every little inch of ground that I could. When you take into account the fact that tidal heating provides conditions suitable for liquid water to exist on the moons of Jupiter, such as Europa, far outside the habitable zone, and that our current number of galaxies is about 25% higher than the number I used, and it is conceivable for a non-G-type spectral star to have a habitable zone, the creationist position begins to look pretty bleak. That is not even accounting for the possibility of some bizarre alien life which relies on, say, methane instead of water, meaning that a good chunk of the moons of Saturn are possible cradles of life, or that some even more bizarre form of life, which doesn't even use any sort of carbon-based compounds, could possibly exist. So overall, my message is this. Don't let big numbers scare you into thinking something is improbable. No matter how improbable something is, in a universe as large as ours, it is pretty much bound to happen no matter what. I hope that this video has proved insightful for you, and I would like to wish you a pleasant day.